would like to thank Professor Nuzu for joining so early in the morning from LVNL, USA. And as you all know, as a part of this school, we have special lectures. There are 4 lectures, so which is starting today. And the first lecture is by Professor Nuzu. And I thank Professor Nuzu again for accepting our request, finding time, and presenting to us in this lecture, in this special lecture. And may I request Professor Raghunath Sahu from CERN to introduce formally today's speaker, Professor Nuzu.
Yeah, so thank you, Siddharth. So welcome all the students and the participants, and special welcome to Nuzu, the special lecture of this evening, and namaskar to all of you, because I believe namaskar is Lorentz invariant in comparison to good evening or good morning, because we are sitting in different time zones. So it is really a pleasure for me to introduce Nuzu, because first we met in 2005 in Bhubaneswar, and afterwards we have been very closely working together, and he has seen the whole progress of LHC India and our participation in heavy ion physics in general. So it is a real pleasure and privilege to introduce Professor Nuzu. And since there are many new students, let me begin with a brief introduction. So Professor Nuzu did his BSc from University of Science and Technology, China, and PhD from Stony Brook, USA. And he has long experience, in fact, postdoctoral fellow in State University of New York in Stony Brook. He was a director fellow in Los Alamos National Laboratory, USA, divisional fellow Lawrence Berkeley Laboratory, USA, adjunct professor. He has been adjunct professor in NICER, Bhubaneswar, since 2015. And for all of us who worked in STAR, it was a glorious time. That beam energy scan was introduced almost during that period. So he was spokesperson of STAR experiment during 2008 to 2014. And then further, he was in PSC of High Energy Physics, Joint Institute for Research, JNIR, Russia, IPAC, Humboldt International Center for FAIR, Germany, President, International Organization of Chinese Physicists and Astronomer, PSC of High Energy Physics, JPARC, Japan. And all of us, we know him very closely who are working in CBM, particularly the CBM collaboration board members. So he has been the chair of institutional board of CBM experiment, and he finished one term and unanimously got elected for the next term. And if you look at the awards, he has plenty of awards, plethora of awards to his credit, but I will just name a few. So he was awarded in 2004, the Fellow of Institute of Physics, UK. 2009, he got elected to American Physical Society Fellow, USA. And he is a member of Academia Europea, UK, in 2018. And if you look at the other works, so he has been a referee in physical review letters, physical review C, physics letters B, which are actually very renowned journals for high energy nuclear physics. You must be submitting your papers to all these journals. And he has been in the editorial board of Progress in Particle and Nuclear Physics, Elsevier, Science, China Physics, Mechanics and Astronomy, published from China, Advisory Editorial Board of Nuclear Science and Techniques. Then he has been in the editorial board for 10 years in Journal of Physics G, Nuclear and Particle Physics, IOP UK. And he's supervisory editor in Nuclear Physics A, editorial board published by Elsevier since 2014. And today we have the pleasure of listening to him on a topic which is very close to all of our hearts. Essentially, all meaning is, the people who are working in heavy ion physics, so namely the phase structure of QCD matter. So with this, with wholeheartedly welcoming Nuzu, very close colleague since a long time. So I hand over the platform, online platform to Professor Nuzu. Yeah, thank you.
Thank you very much for the kind introduction. And I would like also thank organizer for the kind invitation. So that allows me to share some of our recent progress with all of you. This is a discussion what I dear to my heart. So if you have any questions, please raise your hand, and organizers, I guess, will see, and you can interrupt me just like a normal seminar. So don't feel anything, ask questions. I always say there's no stupid questions. I cannot say the same for the answers. So please ask questions. All good students I know are asking always good questions. So please do so. So today I will focus on the QCD phase structure in heavy ion collisions with a selected result from both LHC and RHIC. Although I will mostly use the RHIC data. Yes, I'm from the presenter. Where's my name? Yeah. I'm from Berkeley this year, so next year may be different places. So now let me start the introduction. Let me start with the phase of structure. The phase structure of matter. In physics, what we know is once we understand the degrees of freedom, what is next important is the structure, phase structure. Phase structure actually is important. It tells us where the matter is supposed to be. For example, on the left, this is the phase structure of water. It's very familiar to everyone of us. Although the underlying interaction degrees of freedom is the same, but the structure changes when you change external conditions. When you change the temperature and the pressure, it could be in different state. Just for the familiar case, you see this gas, could be gas, could also be a liquid, it could also be a solid. So this is all described in the phase diagram. So it's a phase diagram is a very important issue in physics, in general speaking. But today we are not talking about just general things. We're talking about phase structure of strong interactions or phase structure of QCD, I want to say. So let me repeat again. I was taught important things we need to say many times. Phase structure is for given basic degrees of freedom. Phase diagram tells us how matter organize or reorganize itself under external conditions. I already mentioned water in case of QCD. But today we focus on the degrees of freedom of strong interactions for the phase structure. As early as in 1953, Fermi, in his note on thermodynamics and statistics, drew the very first phase diagram. What he drew here, this is temperature and this is density. This is the very first drawing. About 30 years later, roughly, and when US is preparing for RHIC, Professor Gordon Bain also hand draw a phase diagram here. You can see this is temperature, this is the density. The difference is very important difference. He put a boundary here. This is called the QCD. Now there's a phase boundary. This is a very dramatic and very important change. So this is almost fixed, the phase diagram for strong interactions since then. Professor Gordon Bain told me once, he said he forgot to patent this plot. Otherwise, he will not only be famous, but also be rich if he patent this plot. Because later on, we all use this phase diagram. So This is physics. Physics always has a lot to do with both theoretical calculations and experiment. So let me start with the theoretical calculations of a phase diagram on the lattice calculations. So this is the temperature, this is what we draw, and as function of a baryon chemical potential. Baryon chemical potential, you can just see as a baryon density. That's all we need to know. So it's just a different. This is density and this is temperature. So you see this is a phase boundary shown here. But this is more complicated comparing to just two-dimensional. It has a lot to do with quark mass. So that's why there's X. There is a third axis is called the quark mass. So on this plane, nevertheless, there's a critical temperature shown here, and also there's tri-critical point. In the experiment, that's you have to measure at a finite quark mass. So this is pointed here. So now for this plot, the takeaway is two points you need to remember. As far I think it's important for the discussion later. Also, I think important for the field. That is QCD transition temperature is 156.5 plus minus 1.5 MeV. This is the truth, and it's already analyzed by many data experiment. So this happens at a mu B baryon density equal to 0. So this is very important. The lattice calculation actually is done most precisely. This is the first principle QCD calculation at mu B equal to 0. Once we know this result precisely, we can do Taylor expansion to finite mu B. After many years of exercises, I'm not going to discuss lattice calculations, but I want to just tell you result. The lattice calculation predict the critical point should be in a region mu B larger than 3Tc. So these two numbers I will use in my talk. So this is the theoretical part. This is state of art and the truth for now. Now, experimentally, how do we do study the QCD phase diagram? Let me say the phase diagram again. So this is the temperature, and this is baryon chemical potential mu B. At mu B equal to 0, we know theoretically calculation tells us the transition temperature is 156.5, as I said, plus minus 1.5 MeV. That's a smooth crossover transition from Quark-Gluon plasma to hadronic matter. At the high PT, high mass mu B region, this is a first order phase transition. And this first order phase transition is from the first, also from the symmetry and first principle. And this is not confirmed yet. Okay, so thermodynamically, if this is a smooth crossover, if this is a first order phase boundary, there must be end point. This point is what I just mentioned, QCD critical point. Okay, so it's very important. How do we study this? Is we do heavy ion collisions, try to produce thermalized nuclear matter. Then we change the beam energy. When we change the beam energy, for example, from LHC to RHIC, beam energy scan to the future FAIR and the NICA, we can scan the QCD phase diagram as indicated here. Now, the red line is actually we call the chemical freeze out. Where we do experiment, we can measure it. So what I am saying is what we measured is along this yellow-red lines. So from this analysis, we try to determine if we can find the QCD critical point. As I indicated earlier, as a mu B over T equal to 3, that's the lattice QCD predicted. The critical point must be larger than this region. We do not know much about this, so in this region yet, but I will discuss a little bit later. Now, you may ask why this phase diagram is very important. And I want to say it is very important because in a very high energy collisions or in a region where mu b is close to 0, the matter we created is related to early universe, where Quark-Gluon plasma is formed and hydrogenization forms, and how the universe is created in evolution. At the relatively lower temperature and high baryon density, this physics has a lot to do with the inner structure of a compact stars. So in some sense, if you're looking at the timing evolution of the universe, this phase diagram is like a bridge connecting us from past to the current existence of the universe, right? And on the bridge, one of the key important is where's a critical point. So because that will determine the structure. This is a milestone of the structure on the QCD phase diagram. Okay, that's why this is so important. If this critical point is identified, then in the evolution of the universe, we will have a point experimentally determined. So that's why this is very important. Yeah, so that is the introduction. Then I will start to introduce a little bit of experiment. I use the RHIC as example. Then I will discuss some physics result. I use two, which I'm very familiar. For heavy ion collisions, I always summarize into 3 C's. One is collectivity. Second one is chirality, chirosymmetry, chirality. Third one is criticality. So today I will only focus on collectivity and criticality. All those are emergent properties of the strong interaction of the QCD. So then I will mention what would be the future measurement. If you have a question, please ask. So again, this is a star detector system. In the heart of the detector system, if you are familiar with ALICE, it's actually quite similar. It's just scaled up by a factor of, in size, by a factor of roughly 5. It's much bigger, ALICE. So this is a little brother. In the heart is a heavy flavor track that determines charm quark or bottom quark, for that sake, hadrons. This is very important. I will talk about it later. Outside the heavy flavor tracker is a time projection chamber. This detector is very important for determining the momentum of the track, the particle. And outside the TPC is a time of flight. Time of flight is used for identifying the particle. For example, positive pions, negative pions, or protons, antiprotons. Then outside is the magnet and calorimeter for this. So the unique property of the star detector is a large acceptance, similar to ALICE, and very good particle identification with uniform acceptance. This is very important for the physics I'm going to discuss. The only limitation for this detector is limited rate. So this is about 1 kilo. So this is for particle identification. We use a TPC to identify particles. But this is positive part and negative part. So this is, you can see it's a proton, kaon, and a pion. And this is negative particles. This is for TPC, and the momentum is determined through there. And from up about 1 GeV, the TPC cannot identify hadron anymore, then we use time of flight. So this is after identification, we can decide the fiducial region. We do physics analysis. TPC give us low PT moment, low PT particles, and the TPC plus time of flight give us a larger PT. Okay, so Then this is the acceptance from different collision energy from 7.7 to 200 GeV. You can see how good this detector is, very uniform for particle identification. And also for given energy, different particles also acceptance rather uniform. This is very crucial, very important. Please remember that good detector is very important, as good as good ideas in experiment. So star energy span covered is from 200 GeV center of mass, corresponding mu B, chemical potential is about 25 MeV, all the way to 3 GeV, with corresponding chemical potential about 750 MeV. So this is the current status. Before I go into special physics point, I want to show you how experimentally we determine the chemical properties. So we take a particle yield, we measure the pion, cation, protons, and lambda cascade. We put all these numbers into thermodynamic equations. There we can determine at least 2 thermodynamic parameters. One is the chemical freeze-out temperature, and this is chemical potential, mu B. So these red points are all from star, central gold-on-gold collision, 0 to 5% collisions. And here at very high energy or very small mu B, 1 MeV, that's from ALICE, lead-on-lead collisions that you're very familiar. Yes. And this is red point is from central gold-on-gold collisions. Open squares are from peripheral collisions. I assume you understand all these terms, so I will just say this word. So, and this yellow line is the empirical chemical freeze-out line. That's what I showed you early in this phase diagram, where the chemical freeze-out line is described. So this is what we know in the phase diagram. This is how do we extract from particle, measure the particle yield, experimentally determine. Oh, I'm going backwards. So yeah, so that is very important. As you can see from this experimentally determined phase diagram, we don't have much data above 400 MeV. And this is also, you see the curve somehow to make a dramatic change dropping here. So this is the region I think important for the future. Now to demonstrate why this region is very important, I use charged cation ratios. This is a positive ratio and a negative ratio. In the positive case, this you can see clearly at 8 GeV, there's a peak. This is a point here. When you go to high energy, you see both ratios approaching to same value. This implies pair production. K plus, K minus, for example, pi plus, pi minus becomes dominant. On the other hand, in the low energy or in the high baryon density region, the something else is important. Here I argue this is because the associated productions, which has a lot to do with the baryon density, that leads to this peak. The associated channel only relevant for positive charged cations. So that's why I use the arrow here to indicate. In this region below 7 GeV, I call 8 GeV. That is a high baryon density region. So this is this idea, of course, is confirmed by theoretical calculation. You see this peak at the freeze out as a maximum baryon density at 8 GeV, 4 plus 4, as shown here. So just remember, at the below 8 GeV is high baryon density. Lattice calculation says only above this 8 GeV, as I said earlier, of mu B over T larger than 3, that possible critical point happens here. Now let me discuss the collectivity. Collectivity, what we do is we expand the as-mutual distributions by the Fourier series. Okay, from this analysis, we can extract the coefficient. For example, V1 is we call directed flow, V2 is elliptic flow, and so on. We have triangle flow, And this is a language in the language of hydrodynamics. Assume the system has reached local equilibrium and collective expansion. Why this is important, I just give you a picture, just help you to visualize the physics processes. You see, in non-central collisions, shown here, in the overlapped region, it looks like ellipsoid. In the collision, in the violent collision, you can see we produced very dense matter through interactions among this produced among these particles in the overlapped region. We will generate the pressure gradient. Then system will expand because this x-axis in this way is shorter. Therefore, the pressure gradient is larger. So on the final state, in the momentum space, in Px it becomes larger and Py becomes smaller. Understand? Because the pressure gradient is larger in x, so Px is larger, and the y is smaller, so Py is smaller. Therefore, we generate anisotropic flow. Here I just show you this is V2. Experimentally, what we do is we just measure Px, Py. Experimentally, sounds very straightforward. So the transition from coordinate space to momentum space anisotropy is determined by the nature of the interaction. To reflect the equation of state of the system. By studying this, we can extract all these important parameters. I show you few examples. I hope you understand. If you do not, I am happy to stop to answer. I show you two plots, one from RHIC, which I like really dearly, and this is one from Alice. It's also very important. From RHIC, I show you this V2 measurement as function of transverse momentum from pions in yellow and protons in red triangles. Pion has 2 quarks, I assume you know, and proton has 3. As you can see in the low transverse momentum region, pion, the value of pion V2 is larger than that of proton. On the other hand, if we go to a little bit higher PT region, this order reversed. Okay, and I use the dashed line to fit them. If you divide this by, for example, V2 by number of quarks and also transverse momentum, you will see a scaling. They're following one same curve. So this is for U quark. I call U quark, D quark, light quarks. Now I make the same plot, but for different hadrons. The yellow here I draw phi. Phi meson has 2 quarks, K SS bar, and omega baryons has 3 quarks. You see the very similar pattern here. I also did the scaling. They followed very well. What does this mean? This means U quark, D quark, and S quarks are all flow, this V2, as I said, describe the elliptical flow in the same manner in the collisions, in gold-on-gold collisions. You may say, okay, this is only for S quarks. S quark is still relatively light, only 200 MeV. How about heavy quarks? This is why I showed at Alice. This is a measurement of D meson. D meson has a charm quark. Charm quark has 1.5 GeV mass. As you can see, in the high PT region, above 4 GeV, the heavy quark hadron D meson flow as strong as at pions, which is red squares. What these two plots tells us that U, D, S, and C quarks all flow together. This is what I call platonic collectivity. All quarks move in similar. In order to have this happen, the system must be in a state, in the mood of deconfinement. That is a very strong signal of the formation of Quark-Gluon plasma. So this is very actually important. Again, I just flash you measurement with star, also measure D quarks, D mesons, which is charm quark. And here we do the scaling, V2 normalized to number of quarks. D meson has 2 quarks, and normalized transverse momentum. You can see clearly the scaling. From this, we conclude local thermal charm quark has reached the local thermal equilibrium with the medium. So that is a clear signal of the formation of Quark-Gluon plasma. We not only measure the collectivity, say V2, we also measure the modification factor called RAA. This is strong suppression in high PT less than 1, also indicative of a strong interaction and the formation of the local equilibrium. That's why this is actually very important. Now, from this, what people may say, why this is so important, what we can learn. So what I can tell you is because of heavy quark is so heavy, much heavier, charm quark is much heavier than the temperature that could reach in such collisions. So this can be used to probe the medium properties. What we do is we put all this measured information, both V2 and the RAA, into theoretical calculation. Then we can extract the heavy flavor diffusion coefficient. As you know, in the Langevin theory, if you do this, you can tell how the medium is performed. From the current data, we can constrain the diffusion coefficient as function of temperature in this order, in the blue and the red region. These are two different calculations. And we know that D sub S is in the region of basically 2 to 4 region from here. Now, from Alice's future upgrade after 10 inverse nanoband data, this uncertainty here will be shrink at least by a factor of 2. So that's the future program. You can see from these references. That's why this measurement is very important. Now, let me basically say this measurement tells us at in high energy collisions where mu b is small, the Quark-Gluon plasma is reached. So, and we know the properties. I'm going to gradually turn into lower energies. So how do we do lower energy collisions? This is a star detector. I showed the picture before. This is engineer picture. Now it's about 4 or 5 years ago, star, we have a really genius collaborators. Put a piece of gold target at the entrance of a TPC. Initially, it's a collider experiment. With this target, we can do fixed target collisions. In order to particle identification, we put a new time of flight wall or end cap on this end. So then we can do a fixed target experiment. This allows us to extend the collision from 7.7 GeV all the way down to 3 GeV, mu b from 420 MeV to 750. So that push star into the high baryon density region. This is very, very beautiful. Here is 2018 data. Do you remember I showed you particle identification? So I'm showing you again here. This is positive part, negative part. Because this is low energy, not as many antiparticles produced. Mostly are positive particles. Kaons, protons, deuteron, triton, 3 helium, 3 helium 4, all the way to lithium 6. And in these collisions, we also construct all these topologically identified particles. This is the particle acceptance. As you can see, the acceptance is different. This is dramatically different from collider experiment. As function of a particle mass, acceptance becomes different. Only pion is very smooth. Another interesting, very important thing is a high baryon density. We also can create hypernuclei. Hypernuclei is not the focus of my talk today, but it's also very interesting. It's a nucleus. Inside a nucleus, we replace one nucleon, let's say neutron, by lambda, called a hypernuclei. This is important if you want to study the inner structure of compact star. The strangeness interaction there becomes really very important. So this is our recent collectivity measurement, V2, as I said already, and V1 from 3 GeV collisions. What you want to know from this is what we found here as no QGP formation. Only hadronic interactions can reproduce from model calculations, reproduce the data. So hadronic interaction is very important. You remember when I said earlier, in V2 measurement, there's a number of quark scaling in high energy, as I show here, from high energy, positive particles and negative particles. But at 3 GeV, this scaling has disappeared. That's why when I plot as function of collision energy, I say that 3 GeV is hadronic matter, and above 7.7 GeV is a QGP, Quark-Gluon Plasma. So that is about the collectivity. So collectivity help us to determine the QCD phase diagram. We know that high energy mu B close to 0 is QGP, and 3 GeV is hadronic matter. So now let's ask is there a critical point, and how do we find it? So in strong interactions, I guess you know, because through these lectures, we know the baryon charge, electrical charge, and the strangeness, they are conserved. With this conserved quantity, we could do the fluctuation studies to extract the medium property called the correlation length of the system. We also know the higher order of the correlation of the correlations, and they're more sensitive. So here I introduced called the culminant. By definition is showing here mean, variance, skewness, and kurtosis. From this moment, it's related to the culminant ratios as shown here. This is experimentally we can measure, and we can connect to theoretically calculate susceptibility ratio. I use the psi here. So this allows us to do direct comparison between experimental moments ratio to the theoretically calculated. I guess intuitively you understand what is the mean, what is the variance. It's well defined, and the skewness describes the how symmetry the distribution we measure. For example, this is mathematically you can calculate the positive, and this is negative skewness. Kurtosis tells you how this distribution at near 0 is peaked, actually determined by the tails. Okay, so this is intuitively you can see. The higher the order, the more sensitive to this. I just draw up to 4th order. Actually, our measurement now already reached the 8th order. So it's very, but today I will only show you to 6th order, I think. Now, theoretically model calculation indicates is, you look at this phase diagram here, if there's a critical point showing here, and the freeze out curve, you remember this red and yellow curve showing here, is along this way. If we do measure this 4th order kurtosis measure as function of collision energy, we would expect along the baseline, there's a drop, then come up again. This is due to the change of the basically interaction length. So this oscillation pattern or non-monotonic behavior is what we are looking for. I should point out 2 things. One is this is ideal case in the infinity system. In real case, in finite system and short duration time, we do not really expect a critical point per se. What we're looking for is this non-monotonic behavior, and with a region, I call it critical region. So number 1. Number 2, this baseline here is ideal one. There's no other dynamics, and that's why we show 1. Actually, the baseline could be different. For example, if we have a baryon number conservation, one would expect the baseline will decrease like this, and I will discuss later. It is indeed the case, but nevertheless, this is what ideally what we would expect to see. So I hope you keep this in mind. How do we do that? This is experimental measured particle, net proton particle distributions, multiplicity distributions, because we cannot measure total baryon, net baryon. We only measure net proton as a proxy for that. For 200 GeV collisions, red crosses here, all the way down to 7.7 GeV, showing here. And you can see two things. At 200 GeV, this mean is almost zero, but not exactly zero. That means that proton, antiproton number close to each other, but not exactly. This is because there's still finite protons from beam coming into this. On the other hand, at 7.7 GeV, the mean is much larger. That reflects there's a lot of protons, more than that number of antiprotons. So that's the nature of this distribution. Now, from these distributions, we can extract the coordinate for this net protons: C1, C2, C3, C4 for central collisions in red, and for peripheral collisions open squares. So those are the distributions. You can see for C1, C2, C3, they're relatively very smooth, but so for C4, we can see this bumpy structure already. And what we normally do is we generate this moment or coordinate ratios. Here is a C3 over C2, and this is a C4 over C2. And just focus on the right plot, as you can see immediately, just by eye, you see there's a clearly deep dropping here, then comes up. And this non-monotonic behavior in central collisions, it's a 3.1 sigma effect in this fourth order. There are a lot of things can be said about this plot. I just want to discuss 2 points. Yeah, here. One is this is the transport model, hadronic transport model calculations with this golden band you can see here, and also shown here. And as you can see, this model has no critical point. Only appears going down is because of the baryon number conservations. The measurement is done in the fixed rapidity window. Therefore, going to lower energy, we accept more and more proton, antiproton. Because we accept more, and then this baryon number conservation effect becomes stronger. That's why this is coming down here. Number 2 point is the current measurement, actually error bar is quite large. The B-man in scan 2 will shrink this uncertainty, statistical uncertainty, to the green band. So we are actually in the future we'll have much better statistics. Last point I want to say, there appears there's a attractive interactions. The suppression is repulsive in general, and this rise maybe indicate attractive. You know, in case, we all know that in case of critical behavior, you need both the interplay between attractive and repulsive. So this already non-monotonic behavior already indicate possible existence of a critical point. Yeah, this is our basically analysis of the data. How do we extract the 3.1 sigma for the fourth order? This is because we actually for third order is about only 1 sigma effect, non-monotonically. For second order is totally monotonic behavior. And model calculation also shows that the higher order, the more sensitive. This data also consistent with that prediction. As I mentioned earlier, we not only measured C4, this is C4 plot as function of charge multiplicity, we also measured C5 and C6. Here I compare this heavy ion collision from gold on gold with proton collisions, which are showing these red dots. You see here, proton collisions for C4 is always positive, C5 also always positive, and also C6. On the other hand, for heavy ion collisions, you see they are progressively becomes negative, as predicted by the lattice QCD calculations. This data statistics still not very good, but this is the very first comparison, direct comparison between experimental data with the first principle lattice QCD calculation. This is very important. Both these indicate that the system is consistent with lattice calculation. For the first time, that QCD matter is produced. This is very, very important message. I hope you can take it away for 6. So is it consistent? Remember when I discussed the collective flow and high energy indicate QGP formation. There we compare to model calculations, not the first principle calculation. Here is the first for the that's why it's very important. Actually, for the C6 over C2, our paper already accepted by physics review letters as of last week. So we are very excited about it. Of course, once we have the data, we always compare directly from lattice calculation. As I showed you earlier, we do Taylor expansion, and this is a fit from lattice calculations. You can see it fits very well up to 20 GeV. So this point is up to 20 GeV. Same for C3 over C1. The reason we cannot fit for this region, this is because lattice calculation is for thermal system, not without a critical point. So this deviation, another indicative of something new is presented. So let me try to summarize in this by discuss a little bit in high baryon density region issues. So let me show you again this C4 over C2, all this kurtosis times variance. We see this looks like oscillation pattern here at a lower energy or high baryon density region. This is the highest published result. We also know at 3 GeV URQMD calculation shown here. That means this come down and goes up and will come down again at the 3 GeV. Another word is this oscillation pattern is very important, is established. Although we have star fixed region from 3 to 7.7 GeV, as I mentioned at the very beginning, discussed with my friend, in this region, only 3 GeV we covered middle rapidity. In other star fixed region, we cannot. Therefore, I argue that CBM experiment in the future is very important. If we look at the QCD phase diagram, what I'm trying to say is up to this point, I think we understand this is dominant by Quark-Gluon Plasma. And we also know at 3 GeV, roughly mu p over T is equal to 7 is hydraulic matter. So real focused region is in this region, mu b over T equal to 3 to 7. And this is where the future star B minus scan 2 and CBM experiment should focus. I think it's very, very nice. So when you have a new physics ideas, normally you have to come up with a new upgrade or new detector. In STAR, we had 3 upgrades. One is the inner TPC, ITPC, shown here. This will extend our rapidity coverage and also DDX resolution, therefore better tracking. And we also have a new end plate event plane detector, new detector. And as I said, we also have an end cap time of flight. All these 3 upgrades are very successfully completed. By 2019, it's all in operation. So, we already took the B-Manu scan 2 actually is already completed by June 21st of 2021 this year. So we already collect all the data. What they were busy now is to process the data and then for analyzing in physics. So I should speed up a little bit. As I promised, I will also mention ALICE. Here's ALICE upgrade. I'm sure many of you are familiar with ALICE. ALICE has taken 2 very important upgrades. One is in the heart of the TPC, there's a inner tracking system. Basically, it's a silicon tracking system, ITS2. This is also already completed and installed. So same as a time of flight, time of projection chamber upgrade. This is basically increase this data taking speed from currently about a few kilohertz to future 250 kilohertz. The future program from Alice is a heavy flavor measurement because of ITS and the dileptons. And I hope we'll also do high moment of that proton. Remember, I said at high energy, mu b equal to 0, that's the best place you can do such high moment measurement comparing to lattice calculation. I think it's really very important. So looking at the collision energy and the collision rates, this is a map. We can have at the high energy end, we have Alice with high rate and the collider experiment. And this future, the rate will be around the 50 kilohertz. And next, other extreme, that's a CBM experiment. You see the collision rate is 10 to the power of 6 or 7 range. This allows us precision determination on high baryon density region. The advantage here is we have a very uniform nice acceptance, and the advantage here is high rate, really high rate and precision measurement. So I hope these two will of course complement to each other. Now, what I think, because you're a student, I want to share with you what I have in mind, what is important observables. At high energy, I think it's very important to study the property of this chiral transition and using heavy flavor and high moments to determine the property how this transition happens. And for this part, of course, this will do high moment measurement. We can do 1 to the even 8th order, and we'll do dilepton invariant mass measurement. So will happen, also will happen here. And here I mentioned earlier, because of high baryon density, we also do hypernuclear production measurement. There we can study hypernuclear and even hyperon interactions in order to infer the inner structure of compact stars. And there are more things, normal things people use, chemistry, space-time extent, doing through correlations and light nuclear productions. And also the alignment issues, which I'm not going to discuss here. So let me summarize what I've said so far. And this is a phase diagram again. At mu b equal to 0, that's formation of Quark-Gluon plasma. And critical point is likely in larger than mu b over t equal to 3 region. And this is where CBM is supposed to really cover. Star BMN scan 2 will cover this region, but we need CBM in order to confirm the first order phase boundary and the QHD critical point. So my heart is future is in this this part. BMN scan 2 from star and the CBM experiment in the next roughly 5 to 10 years. So with that, yeah, this region we know. So this is what I want to say. Now let me say some few acknowledgement. This work I showed here actually has been done since 2008, many years, through many discussions. And most people involved are students. This is Sam Hepperman from UC Davis, and Debashish Malik, I think he's in the audience, student from Bhubaneswar, Sawi Lan, and Risa from Japan. Ashish, I hope he's also in the audience, from also Bhubaneswar, and Yang Zhenzhen and Yu Zhang from CCNU. And we also have lots of discussions with theoretical colleagues. And finally, thank you very much for your attention. That's it.
Yeah, thank you, for the very exciting discussion on a physics topic, which is very close to our heart, essentially exploration of this QCD phase boundary and the location of the possible critical point, and with new detector upgrades, new technologies, new variables, what are the promising physics directions. So I think everybody has enjoyed, and the floor is now open for questions, comments. So we'll start with Nilkamal had a question in between, I could see. I could not stop, so Nilkamal, go ahead if you have still the same question.
Yes, hello, Professor. No, that was really very interesting to see
Why
all the
don't you
results.
switch on your video? That is better for interaction.
Okay, Yeah, so this is me, Nilkamal Malik from Indian Institute of Technology, Indore. First of all, that was a very nice talk that you summarized all the results from RHIC and LHC. And my question is on slide number 13, when you plot V2 as a function of PT for light flavor particles, for example, pion and proton. You saw some dotted line. So is it some function that fits the curve?
Yes, I can. This is we call this is the those lines called the scaling line. We have in I remember it's about 2004. We published a paper on those curves. Yeah, it's a number of quark scaling curves. I can send you the literature to the field.
Okay.
I'm sorry, I did not list the here. Yes.
Yes, I can see that they can nicely fitting the data. So I was interested to know. Okay, thank you.
Any other questions? Just feel free, because we know since more than 2 decades, 1 decade plus. Yeah, just unmute yourself and start interacting. You don't need any permission. It is more informal session.
All good students. They ask good questions.
I have one question.
Yeah, Suman, go ahead.
Sure.
Okay, so I'm Suman. I'm from IIT Indore. So
Switch on your video. Switch on your video so that when No will see you in GSI, he can recall, right?
Okay.
Okay.
Okay. Hello. Hi. So in slide number 18, you were showing V2 plot as a function of PT. There was negative values also were there. If I'm not mistaken, slide 18. So the question was, what is the implication of negative V2s?
Negative V2. Yeah.
Yeah.
Very good question. Yes.
Yeah.
This is a low energy. You can see, so in case of low energy, two nuclei passing to each other, collision happens like this, right? And the event plan is determined by the beam direction and the impact parameters, so Z and X. So we do this way, right? Because now let me turn this way, the two nuclei passing through this way, passing this way. You can imagine this, if its passing is very slow and a collision happens, we generate the medium here. Then this spectators still blocking the expansion in the X direction. Therefore, only way they can escape is vertically along the Y direction. And if you look at my definition of V2, so if you go to out of plane, this V2 is a negative, literally negative. So that's why I want to show you. You can see, I guess. And again, so you can see when you go to V2, and the high energy is positive. Positive meaning in-plane expansion. But when you go below 4 GeV, also you become negative. So this is called a shadowing or blocking effect. Okay.
So beside getting the out of plane, so is it the nature of the event which is compelling it to be negative?
If there's no blocking, expansion at low energy should be more or less isotropic.
Okay.
Yeah, because of blocking, yeah, there's no way to expand in X direction. So blocked. When we observe, this is the X direction is suppressed. In high energy, because they go so fast, there's no spectator, only the overlapped region. Then because the pressure gradient in X is always larger, because X-axis is shorter. That's what I explained, yes.
Yeah, I got the point. Thank you.
Sure.
Yeah, thank you so much.
Which experiment, Suman, you are doing? CBM?
No, I'm in Alice.
You are in Alice. Alice, you will only see positive.
Yeah, that's true.
But I'm telling you, CBM is very interesting. You may find the critical point.
Okay.
Yeah.
Next question is from Minaki. Minaki, would you like to ask directly? You can switch on your video, audio, and interact with No. If you are equipped, otherwise I can read out your question. Okay, so Minaki has a nice question. So first, she thanks you for the nice presentation. And the question is, I have a small confusion regarding two things. One is transition from hadronic to QGP phase and chiral symmetry restoration. Do these happen at same time and temperature? If not, what is the time and temperature difference?
Yeah, thank you for this question. And but I have to say this question, I do not know the answer. I only can repeat what I learned from theory. There is a difference, and in terms of temperature, as I showed the lattice calculation at the very beginning, the chiral transition, there is a chiral transition temperature. Chiral transition temperature is about 130 MeV. The QCD phase transition temperature is 156. So that is a lattice result. So I just told you the difference. What was next? The second question, second part was, does this happen? Yeah, whether they happen in same time or not, I do not know how to answer because I don't know how to detect that. Okay, so yeah, but according to lattice calculation, at mu b equal to 0, the transition is chiral transition. It's a smooth crossover. It's very broad. Whether it happen, I think it's difficult to say whether they happen at a different time. I do not know actually how to precisely answer this. I suggest you ask Professor Surendra Gupta from ITFR. So he is very knowledgeable. Surendra Gupta, ask him. So, yes, but don't tell him I suggest you to ask him. Yes.
Okay, yeah. Thank you, Minaki. Nice question, but looks like it is little difficult. Yeah.
Yeah, I do not know the answer. Yes.
And next question is from Ronald Scaria. Ronald, would you like to ask directly? Switch on your video, audio. Go ahead.
Hello, sir.
Hello.
Am I audible?
Yeah.
Yes.
Go ahead.
Okay. So my question was, in your second or third slide, you had mentioned that, while you were explaining, you had mentioned that determining the critical point is quite important in understanding the evolution of the universe. So
Yes.
can you elaborate on that? That is my question.
Yes. Thank you. In evolution of the universe, imagine there is a critical behavior. What is a critical behavior? Just from mathematically, critical behavior means you have a long range correlation, the whole system, the long wave things. So this, you can imagine this will change the whole evolution of the, just imagine the case we do have a critical point system stored somewhere there. The simplest, what will happen is the pressure gradient will not change for a moment because you are in this long mode. Then the time will change, all things will change, I think. I don't know if we can determine experimentally critical point, but if we do, my feelings, all the calculation will be redone again. We keep that in mind. So that I think it's quite important. So that's why I encourage bright young student, if you're smart, join us, determine this point, your data will be point in the evolution of the universe. You know, how many years universe already? We only live, let's say, maximum 100 years. But if we have that point, you will live forever. That's how exciting it is. It's very interesting. You can, as I said, I put, of course, a little bit dramatic. The QCD phase diagram is a bridge linking from beginning Big Bang to impact compact star. But the critical point actually is the linking point, key point for the QCD phase diagram. Yes.
Thank you, sir.
Thank you.
Thank you, Ronald. So next question is from Priyansi Sinha. Priyansi, would you like to switch on your video and audio and interact? Yeah, please go ahead.
Hello.
Hi.
Yeah, hello, sir. It was an excellent talk, very comprehensive. My question was in the ratio for K pi, in one of the slides, you showed that the peak or the bump is because of the associate production, but that's only for the positive ones and not affecting the minus, the negative particles. Can you just elaborate on that? Why is it?
Sure. Thank you for the question. Yes, that is because at a low energy, in a production of I don't know what happened. So in a production, K-ion production, in K-ion production, K plus, the K plus is produced by the two possible channels to produce K plus. One is called a pair production, K plus, K minus. And another channel is called associate. Nucleon collisions go to nucleon plus lambda plus K plus. In terms of pair production, okay. In terms of pair production, somehow the PowerPoint keep dying. That must be related to your questions. So, in case of K plus production, is associated with K lambda and the nucleon. So it has a lot to do with nuclear compression. But for K minus, it's not associated because it's a pair production. It doesn't matter what happens in the nucleon part. That's why K plus shows density dependent, and K minus shows a smooth increase, like any particle production cross section. So this only happened near threshold at the low energy collisions. At high energy, pair production becomes dominant. That's why this is the data. This is data for we know for many years. So for many years, and yeah, this is current explanation. I hope it's mostly. I have been fighting for this point for almost 15 years. So, yes.
Okay. And just one another naive question. So there were various cumulant ratios that you showed, which were showing the dip, particularly the higher one, C480. So how is it decided which ratio to take essentially? Like there was C4 by C2, C2 by C1 also. Like how is it decided as to which will give us a physics implication?
Right. Very good question. Thank you. And in principle, actually, I do not know. In what we argue is the following. It's actually all this is done theoretically. I should have shown a theory curve. It's all oscillating around TC, the calculations. What we look at is for characteristics where they are. So for example, for C6 and C5, we know from lattice calculation, around TC, they are all negative. Okay. For mu b equal to 0, I need to emphasize for lattice calculation, we only precision and first principle calculation is for mu b equal to 0. So around TC, then we look at this behavior. For example, C6 is a minus 1.5, C5 is minus 0.5, C4 is positive. You see this progression showing here, and this is characteristics we look at it. For example, I cannot do this for 3 GeV data because 3 GeV mu b is too large, so I cannot do the comparison. That's not fair. But here, I think it's a very fair comparison. If you are in ALICE, I think I would strongly suggest do this measurement, and you will see, I would say the comparison will be even more fair and more valid, but you will only confirm this. But for at CBM, future CBM, for STAR, our experiment is over. I don't want to encourage you anymore, but for CBM will help us to determine a critical point. That will make you more famous.
Okay. So I'm in STAR collaboration right now, so I'm hoping to do both, maybe to get the critical point.
Do both.
A BS2 in CBM maybe for that region.
Yes, that will be very good. CBM will be online in 2025.
Okay.
So get graduated, join CBM.
Okay. Thank you so much.
Thank you.
PhD in STAR and postdoctoral fellowship in CBM will be really a good drive towards critical point.
Yes. Now I'm forming groups in GSI, and we have students analyzing STAR data and participating CBM detector and simulations. Yeah, that's our current effort. Yes.
Okay, so thank you, Priyansi. I think there is one more interesting question from Minaki. So the question is in the chat box. Another question related to V2 behavior of baryon and meson, and you have explained it by quark coalescence. Can this quark coalescence happen in high multiplicity small system, or is only in QGP phase? So I think she is referring to high multiplicity PP events at LHC, and question is on quark coalescence.
Very good question. To me, if I understand properly, coalescence actually for hadronization is almost universal. Universal in the following sense. I guess you may know this Lund calculation called the Pythia. In that case, the hadronization happens called the string fragmentation. What string fragmentation naively in the picture is you take an energetic quark. You take an energetic quark that you can, from vacuum, you pop up quark anti-quark pair. Then this one of the quark from the pair will combine with this quark, form hadron, let's say pi. This is the form. This is the coalescence. What the difference in heavy ion collisions is when we do combination, those quarks not necessarily only from a single string, a single quark could come from another different energetic quark in heavy ion collisions. I would say yes. If you have lots of data, you can do this test. But I don't recall, I do not remember such analysis. In STAR, we did not have a PP collision such, but for LH, if you are doing LHC, try that. That's very, so I think it's universal. In terms of PP collisions, high multiplicity, I know almost everything is reproduced except jet quenching. But theory calculations say still that the jet quenching must be there. You just need to find it, according to Woos-Wiedemann from CERN. So yeah. Okay, yeah. I hope I answered this. Yeah.
Yeah, I think the jet quenching results in PP high multiplicity in ALICE is null results so far. If I know or recall.
That's true. That's true. That's why Bruce said it is there. Just find it. By definition, it must be there. So that part I do not know. I cannot answer jet quenching questions.
Yeah. Okay. So any more direct questions? I think Hirak has written one in the chat box. So Hirak, you can unmute yourself and ask the question directly.
Actually, sir, here is too much noise.
Okay, okay. So I will read your question.
Thank you, sir.
Fine, fine. So your question is, I got the point how even pair ratios are connected to lowest even pair ratios. That is kurtosis times variance. So is the question clear? No, it's not.
Sir, I am sir telling sir. Sir, my question is, sir, is this possible to see the sinusoidal like modulation around the critical endpoint in case we determine the higher order cumulants like C4 by C2 or something like C5 by C1?
Yeah, I missed your first part of the question. I think it is clear now. So the question is this possible to see sinusoidal like modulation around the critical endpoint in case we determine higher order cumulants and their ratios like C4 by C2 and C5 by C1? Yeah, so that is the question.
Could you say it again, the first part?
First part is it possible to see sinusoidal like modulation around critical endpoint in case we determine higher order cumulants like the ratios C4 by C2, C5 by C1 and all that?
Yeah. I still don't get it. What is the first? What is oscillation? You say modulation?
Yes.
Sir, actually, I see a curve where you showed that there is a sinusoidal like behavior with the baryon chemical potential. In your PPT, sir.
Do you remember which?
It's like slide number 18 or something else.
I'm trying to go to 18, see what happens.
Okay, sir.
Oh, my PowerPoint is complaining again. You say, is that right? My question is it possible to see the sign oscillation if there's a critical point? Is that what you're saying?
Yes. Yes, sir. Actually, there is a curve. This is going upward and through the critical endpoint. You see that there is a critical. There must be a critical endpoint where it passes through and goes down.
Is this what you mean? This oscillation?
Yes.
Here? Yeah, that is exactly what I said we would like to see. This oscillation, and if you join me to CBM, we will determine where the peak is. Actually, CBM, I think peak is around somewhere here, and we need the CBM to determine. For this point, 2.4 GeV and 3 GeV goes down for sure. We know we have data consistent with URQMD. So, but what we do not know in this region, yes, we already have the red part confirmed. Now it's a blue part where the peak is. The answer is yes, we should be able to determine. Yeah.
Hello, sir. My question is that the kurtosis times of variance is related to like C4 by C2. The cumulants, ratio of cumulants, sir. Actually.
Yeah, this is the C4 over C2.
Yes, sir. Yes, sir. My question is that if we measure C5 by C1, something like that, the ratios, other ratios, can we see this sinusoidal like modulation?
Okay. From the calculation, I did not show. For example, we know as function of energy, we do not expect oscillation for both C5 over C1 and C6 over C2. They indicate before hit the critical point should be negative. We already have data on that. I did not show, but actually we do have data on that. Yes, our data are consistent with they are negative.
Okay, so thank you, Hirak. I think we had very nice discussion with very interesting and encouraging questions, mostly out of the box questions more often. So, so I take this opportunity on behalf of STAR, Alice, India collaboration, and all the students to thank you, No, for spending a very useful time and out of your busy schedule. And it was really wonderful to meet you virtually. And thanks a lot for your wonderful presentation.
Thank you all, and I hope we will see each other face to face. And I hope some student can join us to the CPM experiment. Yes, I hope see you there. So
yeah.
Okay.
So,
Thank you
so much. Thank you so much.
Bye.
Yeah. Thank you.
Yeah. Goodbye.
Bye.